Let's quickly look at some examples of feedbacks, and starting with the energy balance, which we have already done, but just in case somebody is watching just this podcast for whatever reason. Let's remind ourselves that we're on a sphere and the sun is far out enough that the rays coming in are parallel. So the energy intercepted from the sun is the projection of the earth, which is a circle, like flashing a light on a ball and looking at the shadow. But the amount of energy received per unit area in the low latitudes will be higher than at high latitudes because of these curvatures of a sphere. That gives you colder temperatures and then adds snow and ice and so on, which also begins to reflect more of the sun's energy. They are more reflective than darker land and ocean parts. Hence, you cool it, and the outgoing energy is in long waves, as we talked about, compared to the short wavelengths in the visible from the sun, where most of the energy is reaching Earth, the surface. So you end up with gaining more energy in the low latitudes than you are losing to space, whereas at high latitudes you lose more energy to space than you are receiving. So if you don't do anything, the poles should get colder and colder, and the low latitude should get warmer and warmer. But that's not what happens. So, which means you are probably moving energy from regions where there is excess energy to regions where there is loss of energy. And that along the way produces the weather and climate that we talked about, and then atmospheric circulation that we talked about. Atmosphere, the winds begin to drag the ocean and produce upwelling in the equatorial regions, in the coastal regions, other processes of producing photosynthesis and primary production in the ocean and on land, and so on and so forth. So all these begin to change the albedo, the water vapor, and the whole feedback loop starts. So outgoing long wave and incoming short wave can be thought of this way. We can see this because it's in the visible. So but just by looking at it, we know that it's hot and it's going to burn you. But this part is hot and yet you cannot see it, but if you go close you can feel the heat coming from it, just like our body emits infrared energy that we are not evolved to see, right? So that's the energy balance. Incoming short wave has to be balanced by outgoing long wave for the climate to remain steady. So what we are doing with anthropogenic activities is basically add greenhouse gases which trap the outgoing long wave. They allow the short wave to come in, but they trap the outgoing long wave. That changes the energy budget and begins to warm the atmosphere and land. Okay, we'll look at some of those. So Earth system then is a definition that requires some thought, because system is intuitively obvious. You can think of our own body as a system. We have the digestive system, we have the skeletal system, nervous system, endocrine system, and so on and so forth. They all work together to make us function and wave our arms and talk and so on. So Earth has glaciers, land, ocean, atmosphere, and so on, and there are all these processes: sea ice formation, glacier formation, plate movements, sea floor spreading, volcanic emissions, evaporation, precipitation, winds, and so on and so forth, going from tropics to high latitudes. And here are the greenhouse gases which are going to determine the energy budget of the Earth. The best way to think of it is that Venus is some 460 degrees, Mars is minus 50 degrees, and the difference from Earth cannot be explained just by the distance from the Sun and the energy received. It can only be explained by the internal feedbacks. So Venus has had a runaway greenhouse effect by trapping all of its energy. Mars has been losing all of its energy because it doesn't have a strong greenhouse effect, whereas Earth has this greenhouse effect which keeps water in solid, liquid, and water vapor phase. Is it important for life? Now you read all the time that evidence of water and ice is found on the moon, on some moons of Jupiter and Saturn, and maybe there is life there, and so on and so forth, right? So we don't know, but nonetheless, water could be a critical element for life. So the definitions of forcings, interactions, and feedbacks will be important in the Earth system, because the Earth system, or any system, is defined by these feedbacks and the components working together to produce something that cannot be produced just by one component itself. Okay, so the forcings here, changes in the plate tectonics. So when plates move, you change mountains, you change oceans, you change circulation, radiation balance. Changes in the Earth's orbit, which we will look at. Earth has an elliptical orbit with a tilt and a precession. They all change on some several thousand-year time scales. They can change the energy coming in or the seasonal distribution of the energy, which produces internal changes. And of course the sun itself is evolving over time and has decade to decade variabilities, for example through sunspots, right? When there are more sunspots, actually radiation increases, and when there are fewer sunspots, radiation actually decreases. But sun was 30% less luminous when the solar system formed, so sun's luminosity increases over time, basically because hydrogen fusion is happening as a nuclear reactor producing energy. But fused hydrogen produces helium, which is heavier, increases the gravitational pull. The thermal energy expands the sun, so net effect is that the sun is slowly expanding and becoming more luminous. So in about 100 million years, all the water on Earth should be evaporated. That's how hot it will get. And about 5 billion years, sun will disappear. So that energy is forcing the atmosphere, vegetation, ice, ocean, and land, and they interact with each other and they feed back to each other. For example, vegetation controls the reflectivity or the albedo and the water vapor, so it affects the atmosphere and microclimate, rain. Atmosphere affects ice and glaciers. Ice and glaciers affect the ocean. Ice formation leaves the brine behind, remember. Ocean affects the land, land affects the ocean. So you can see that there are lots of internal interactions, which means one affects the other, but feedbacks, which means the other then affects the original perturbation back. So you end up with climate variations as internal responses, natural variability, changes in the atmosphere, changes in ice, vegetation, and so on and so forth. And various time scales emerge out of that, because ocean has high heat capacity. It's several kilometers deep. It can take energy and store it for a long time, hundreds and thousands of years, and give it back. So it can produce these very low time scales, whereas land and ocean, land and atmosphere have low heat capacity, and they have no way of storing too much energy for too long. So ocean controls most of the low frequencies. Of course, glaciers can do the same thing. Glaciers can keep locking up the water and increase albedo, and it takes energy to melt them. So they also provide low time scales. Okay, so different components have different response times, as we know. Atmosphere, hours to weeks; land surface, hours to months; ocean surface, vegetation, sea ice, and then there are very slow responses like deep ocean, ice sheets, and mountain glaciers. The system has multiple time scales, multiple feedbacks, and so on, and all these together determine not only natural variability, even if humans are not doing anything, but also the response to human activities, because humans most importantly are changing greenhouse gases, but we are also changing vegetation, we are urbanizing, we are changing the ocean, coastal oceans, and so on and so forth. We are changing aerosols, clouds, reflectivity, and so on. So we are perturbing multiple components of the Earth system, and the internal feedbacks that work under natural variability also work with other perturbations like from humans. And our problem is to understand what the net effect of this perturbation will be. Will it be rapid warming? Will it be cooling? Will it be like a thermostat and no change? That's what we have to figure out.